Welcome to The Explainer. Right off the bat, I want you to just take a quick second and look at the device you're watching this on. Whether it's a smartphone in your hand, a tablet, or, a massive desktop setup, the battery charging it, and literally the entire electrical grid powering your neighborhood all rely on the exact same physics. And the wildest part? The foundation for all this modern tech wasn't discovered in some high-tech Silicon Valley lab. Nope. It was found in a relatively simple 19th century laboratory. Today, we're going to unpack the invisible force that quite literally powers our entire world. It's a pretty fascinating question, isn't it? How exactly does just weaving a magnet around scale up to power the whole modern world? Well, we're going to start small, like very small. A tiny magnet in a quiet room, kind of small. And from there, we'll trace that exact same scientific principle all the way up to those massive, roaring power grids that keep our cities glowing at night. Okay, let's dive into this. Here's our roadmap for today. First, we'll look at the spark of induction. Then we'll break down Faraday and Lenz's laws. Third, we'll examine the anatomy of a generator. And finally, we'll wrap up with transformers and modern power. All right, Section 1, the spark of induction and Faraday's 1831 discovery. Let's set the scene here. The year is 1831, and we're in the cluttered laboratory of Michael Faraday. Imagine a breakthrough setup, a simple bar magnet being held in a hand, moving toward a coiled-up copper wire. Hooked up to this is a galvanometer, which is basically just an instrument used to detect really tiny electrical currents. What Faraday discovered here was absolutely revolutionary. When the magnet just sat there next to the coil doing nothing, absolutely nothing happened. The needle stayed dead center at zero. But the very moment there was relative motion, like when he pushed the magnet into the coil or pulled it out, boom, the needle deflected. The motion itself was actually inducing an electric current. The huge, profound takeaway here is that motion equals electricity. That little coil of wire essentially behaves as an EMF, an electromotive force source, magically converting mechanical movement directly into electrical energy. And here's the really fun part about this. The speed absolutely matters. If you thrust that magnet into the coil super rapidly, you get a massive spike in current. The faster the movement, the stronger the push on those electrons. But, and this is crucial, if you slow down and completely stop the magnet, zero current, right? A stationary magnet, I don't care how strong it is, does absolutely nothing. It is the change, the motion, that creates the spark. Moving right along to Section 2, Faraday and Lenz's laws, the rules of induction. Now, to scale this tech up from a single wooden desk to powering an entire metropolis, we need some mathematical rules. Formally, this whole process is called electromagnetic induction. Basically, it's the phenomenon of generating an electric field by varying a magnetic field with time. I really want you to remember that phrase, varying a magnetic field with time, because that invisible, constantly changing magnetic flux, that's the exact physical force currently pushing the electrons through the copper wiring in the walls around you right this second. Now, what's really interesting about this next bit is how elegantly this formula, Faraday's law of induction, captures reality. Okay, I know it might look a little intimidating at a glance, but let's just break it down. That weird E symbol on the left, epsilon, that's just our generated voltage. N is simply the number of turns in our wire coil, because more loops mean more power. And that fraction part, the d phi over dt, that's really just the fancy mathematical way of saying how fast the magnetic field is changing. So this formula explicitly proves exactly what we just talked about. The speed of that changing magnetic flux strictly dictates your power output. But you probably noticed that little negative sign hanging out in the equation. Well, that negative sign is actually so important it gets its very own name, Lenz's law. So while Faraday's law tells us how much voltage is created, Lenz's law tells us the direction. It states that the induced current will always flow in a direction that opposes the very change that created it. Think of it kind of like built-in resistance, which engineers often call back EMF. So if a motor is spinning and doing work, it's actually acting like a generator too, creating a back EMF that literally fights against the input voltage that's powering the motor in the first place. It's just nature's way of always balancing itself out. Which brings us to Section 3, anatomy of a generator, where we talk about scaling up power. Let's see how this all builds into the massive machines we rely on today. Basically, we've engineered Faraday's concept. Instead of just moving a little magnet in and out of a coil, we are now taking a rectangular loop of wire and rotating it steadily inside a super powerful permanent magnetic field, right between a north and a south pole. As that loop spins, it continuously cuts through those invisible magnetic flux lines, converting that rotational mechanical energy directly into alternating current. And engineers actually use something called Fleming's right-hand rule to easily figure out the exact direction of that induced current, just based on the motion and the magnetic field. So the crucial point here is really understanding the two main components of any real-world generator. First, you have the field winding, which is essentially the magnetic field creator. It's what provides those crucial invisible flux lines. And then you have the armature winding, which is your energy conversion point. The armature is where all the actual action happens. It's the part that cuts the flux lines and carries the main load current. The best way to remember it is like this. The field winding sets the stage with magnetism, and the armature captures the energy. But, well, here's the catch. To create the massive, city-powering magnetic fields that we need for modern grids, permanent magnets just aren't going to cut it. They aren't strong enough. So we have to use electromagnets. And this is exactly where excitation systems come into play. These systems essentially pump a highly regulated DC current directly into the field winding to create a truly gigantic magnetic field. By controlling this DC current, prime movers, we're talking massive wind turbines, hydro dams, steam turbines, can precisely control the megawatt load and the output voltage of the generator. And these exciters can be rotating systems mounted right on the shaft or static systems capable of handling up to 10,000 amps of current. That's a whole lot of power. All right, our final stop, section 4, transformers and modern power, reaching your outlet. So we've generated all this massive power, but how do we actually transmit it hundreds of miles without losing a ton of energy to heat? Well, imagine a solid metal sheet moving through a magnetic field. Because it's a solid block of metal, the induced current doesn't just flow in a nice, neat, straight line. Instead, it creates what we call eddy currents. These are basically circulating, whirlpool-like loops of electricity inside the metal itself. And this perfectly illustrates a huge problem, because these eddy currents are incredibly inefficient. They rob the entire system of energy and create massive, massive amounts of unwanted heat. So, to transmit power efficiently, we run the alternating current from the generator into a transformer to step the voltage way, way up. The transformer uses the exact same principles of induction we've been talking about, transferring power from one coil to another through a magnetic core. But to fight off those nasty heat-generating eddy currents we just mentioned, engineers use an absolute genius trick. Instead of a big, solid block of iron for the core, they use ultra-thin, laminated sheets of cold-rolled silicon steel. We're talking usually just 0.25 to 0.50 millimeters thick. By slicing the core into these laminated layers, they physically break up the path of the eddy currents, which drastically cuts down on electrical resistance and energy loss. It's honestly, truly amazing to think about. Every single time you flip a light switch, you are completing a circuit that relies on a principle discovered nearly 200 years ago by a guy just playing around with a magnet and a coil of wire. And as we pivot toward wind, solar, and a greener future, the core technology remains exactly the same. Which leaves us with a pretty thrilling thought. How will Faraday's foundational 19th century principles continue to adapt and scale to perfectly power tomorrow's incredibly complex renewable energy landscape? Something to think about. Anyway, thank you so much for exploring these slides with me today. Stay curious, keep learning, and I'll catch you in the next explainer.